i.e., we're going to look at specific heat today, which is another physical property of all matter. It's called specific heat. And specific heat is defined as how much heat it takes to move 1 gram of something up 1 degree Kelvin or Celsius. Specific heat is unique to all compounds. For example, water has a very high specific heat. If you are going to boil a pot of water and you get it from your tap at home and you put it in the pot and you turn the pot on and you stick your finger in right when you turn the pot on, you will not burn yourself because water takes a long time to heat up and cool down. That is because it has a specific heat that's very high. Just like here where you live in Lakeville, when the temperature dips below freezing, the first night does the water on Lake Marion freeze, and of course it does not freeze, it does not turn to ice because it takes a long time to do that. Water's got a very high specific heat. Lots of other things have low specific heats, like metals, for example. Metals like aluminum or copper are often used as metals when you cook because you want to transfer that heat from the flame to your pan and to your food very quickly. So metals tend to heat up and cool down very, very fast. Okay, so metals have low specific heats, and water has a very high specific heat. Every compound has their own unique specific heat. Again, it's how much energy it takes to make 1 gram of something go up 1 degree Celsius. And the equation for specific heat can be easily calculated. The equation is Q equals mc delta T. Looks like Q equals m cap, meow. And the way that it works is that the Q is the energy, and that's written in joules. Joules. That's how I measure energy in chemistry class, joules with a J. M is the mass. Mass is in grams. C is the specific heat. It's a property that people already know, and you could look up for any compound in a table online. You could find specific heat. So specific heat, and the specific heat of a substance is measured in joules per gram times Celsius or Kelvin. That's the label. So if something had a specific heat of 4.18, you would say, oh, it's 4.18 joules per gram times Kelvin. Just like the label for how long this piece of paper is 8 inches. The label for specific heat is joules per gram times Kelvin. You don't put numbers in there. That's just what the label is. And then delta T is change in temperature. Delta means change and T means temperature. So this is one variable. Count it as one thing. Change in temp. And you can measure it either in Kelvin or Celsius. But another way of writing it is final temp minus initial temp. Means the exact same thing. Change in temperature. So that's specific heat. That's the equation. Q equals mc delta T. In this class, you don't need to memorize any equations. You'll always have them for you, but this is a good one to know because you use it a lot. So here's 3 common problems you might see for specific heat, and we'll show them right about and show them to you with the math. Please pause if you need to write some of them out. Okay. So the first one. How many joules are required to heat a 25 gram sample of aluminum from 28 to 58 degrees Celsius? The specific heat of aluminum is listed here at 0.897 joules per gram times Kelvin. You can solve this any way you want. Okay, some people like to rearrange the equation first. Some people like to shove the numbers in there first. It doesn't matter to me. You just do whatever you're comfortable with. For me, I'll just show you a couple of both so that you get the idea. I tend to like to rearrange the equation first, but I know that's not everyone's cup of tea, so whatever works for you. How many joules are required to heat a 25 gram sample of aluminum? The specific heat of aluminum is this, from 28 to 58 degrees Celsius. You're solving for joules. That's the Q. So you don't need to rearrange this equation at all. Just plug in Q equals mc delta T. I'm going to shovel the numbers in there. So the mass of this sample is 25 grams. The specific heat of aluminum is 0.897 joules per gram times Kelvin. And the temperature change, I mean, you can do this part in your head if you want. It's 58 minus 28, but you can write it out too. That's going to be 30, of course. So if you simplify, you're going to have something like 25 grams times 0.897 times 30 degrees Celsius, okay? And when you do all that math, you're going to get 672.75 joules. Sometimes joules is written in kilojoules, because a joule is actually not that much energy. It's like a quarter of a calorie if you are thinking about food. So this is not a lot. So instead, sometimes it's written as kilojoules. You want to write it in kilojoules, you just move the decimal place from joules, which is the base unit, to kilo, which is 3 steps to the left. And so this is the same thing as saying 0.672 kilojoules. Either one, of course, works for this class. So there is the first kind of problem. So like basically shove the numbers in there and hit calculate. The next one, again, don't forget to pause. What's the specific heat of a 50-gram sample of an object if 2.58 kilojoules is absorbed, raising the temperature 71 degrees Celsius? Okay, so in this one, it reads a little bit different. You can see it's listed in kilojoules. The reason that you'd even want to know this is because you can look up at a table, if you had a thing that you didn't know what it was, and you transferred some energy to it, you could figure out what its specific heat was and then look it up in a table and find out the identity of the substance, just like you can with density, okay? So in this one, I'll rearrange the equation this time, but you don't have to. You can plug it in directly. What is the specific heat of a 50-gram sample of an object? 0.58 kilojoules absorbed, raising the temperature 71. We're already given delta T here. There's no initial and final. It's just told to us this is how much the temperature changes. So we don't need to do anything with that. We're going to plug that in for delta T. I'm solving for specific heat. Q equals mc delta T. Again, it's not bad just to rearrange first. I'm solving for C, specific heat. So I divide both sides by m and delta T. So they cancel out and I get Q over m times delta T equals C. Simple rearranging before you can plug numbers in. It just saves a little bit of time. You don't have to do it that way. You can plug the numbers right into Q equals m times delta C and then go from there. That's fine. So I've got to plug the numbers in now. Let's see. The Q is 2.58 kilojoules. You got to convert that to joules. So that's 2,580 joules. The mass of the sample is 50 grams. And the temperature change was 71 degrees Celsius. It went up 71 degrees. So do the bottom part first, although technically it doesn't really matter. Shove the numbers in, and you will find that you get, let's see, specific heat equals 0.721 joules per gram times Celsius or Kelvin. You can use either one. Doesn't matter if it says Celsius here. Kelvin also works, which we'll explain why later. But that's the answer, 0.721 joules per gram times Celsius. And then again, the reason that you'd even do this is maybe you don't know the identity of the substance. Now you can go onto a table on the interwebs and then find it, look it up, and see what substance this is. The most, I guess, math-intensive kind of problem, and I'll do this your way, but you can rearrange also, are these final temp problems. What's the final temp of a 30-gram object that absorbs 750 joules of energy if the initial temp is 30 and specific heat equals 1.23 joules per gram times Kelvin? So I'm looking for final temp in this equation. Remember, Q equals mc delta T, but delta T really is final minus initial. Final minus initial. I'll do it your way in case, well, I mean your way when I say most students like it this way. I think it's easier to rearrange, but I'll play by your rules. Final temp, we're going to get there. Let's plug all the numbers in first. It is 750 joules of energy in the problem. the initial temp. We'll save that for later. It's a 30-gram sample. There's your M. Your specific heat is 1.23 joules per gram times Kelvin. And I'm looking for final temperature. The initial temperature is 30 degrees Celsius or Kelvin. I guess let's make it Celsius there so we're all on the same page. If you like to do it where you simplify, then you can simply rearrange to do that. Or just like, you can just do some numbers. Of course, my calculator died, so I'm sorry that you have to wait for this. Hi, sorry. So now that you have the calculator, you can do the numbers directly. You might want to simplify, like take these two and simplify them. 30 times 1.23, and you get 36.9. 36.9 times final temp minus 30 equals 750. And then you divide both sides by 36.9. So 750 divided by 36.9 is 20.33 equals final temp minus 30. And then you want to get final temp by itself, so you add 30 to both sides. And you get 50.33 degrees Celsius is your final temp. Any way you want to do it is fine. That way it has, I think, more calculator, more steps, but students seem to like it that way. So, I mean, but you can rearrange it first if you wanted to. If you rearrange it first, you're just going to say Q over M and C plus initial temperature equals final temperature. Either way, it works fine. You're going to get the same answer either way you do it. I don't know why I squared that one because I'm not very good at this, but there you go. 3 common problems for specific heat. Again, specific heat is just a measure of how much energy it takes to move the temperature of 1 gram of a substance up 1 degree. Useful for identifying substances. It's a physical property just like density. This has been my TED Talk. Thanks for coming. Like and subscribe. Bye.